Good morning, everyone. Thank you for joining us today. We're about to dive deep into a world that's all around us, but remains almost completely invisible. This is the incredible realm of nanotechnology, a place where the fundamental rules of how matter behaves can actually be rewritten. It's a foundational science that is already reshaping our lives, and believe me, it's just getting started. From the life-saving medicines we rely on to the very electronics in our hands, its impact is absolutely profound. So our goal today is to really get a handle on its core principles. And to truly grasp this revolution, we have to start at the beginning, with the single visionary idea that sparked it all. The whole journey really begins here, with this amazing quote from the visionary physicist Richard Feynman. Back in 1959, he imagined a future where we could manipulate individual atoms. And his words, "There's plenty of room at the bottom," perfectly frame our topic today as a frontier of discovery. The journey from that initial vision to today's reality is just incredible. Let's start with the most fundamental question. What exactly is nanotechnology? That's the absolute perfect place to begin. Fundamentally, nanotechnology is the science, the engineering, and the technology that's all conducted at what we call the nanoscale. Officially, that's defined as the range between 1 and 100 nanometers. But here's a really critical point I want to stress right away. The common misconception is that nanotechnology is simply about miniaturization, taking something big and just making a tiny version of it. Well, that's not quite right. While smallness is definitely a feature, it's not the goal. Instead, nanotechnology is about the precise manipulation of individual atoms and molecules to construct entirely new materials, new devices, and new systems that have fundamentally different functions and properties from their bigger counterparts. And this really gets to the heart of it. We're building from the very foundation of matter to create things that just wouldn't be possible otherwise. Think of it this way. Imagine not just carving a statue from a block of marble, but being able to place each individual marble molecule exactly where you want it, to create a material with properties that you've designed from scratch. That's the paradigm shift we're talking about. So when you hear the word nanotechnology, don't just think small, think new. Think purpose-built from the bottom up. It's all about leveraging the unique physics and chemistry that only emerge at this incredibly tiny scale to unlock capabilities we've never had before. And this approach is what makes it such a foundational, enabling technology across pretty much every scientific and industrial sector you can think of. I love that distinction. It's really about building, not just shrinking. That's a huge shift in thinking. So let's talk about the nanoscale you mentioned. It sounds impossibly small. Can you give us some perspective on what that actually means? It's a scale that can be really difficult to wrap your head around, so analogies are honestly the best way to build a mental model. Okay, so a nanometer is 1/1000th of a meter. To start our journey down in scale, let's begin with something familiar, like a single sheet of office paper. That very thin sheet is about 100,000 nanometers thick. So we're already talking about a scale far smaller than what we can perceive. But believe it or not, we need to zoom in much further. Now let's take something even finer, a single human hair. It's roughly 80,000 to maybe 100,000 nanometers wide. So the thickness of a piece of paper and the width of a human hair are, relatively speaking, kind of in the same ballpark. Nanotechnology operates on a scale that is thousands of times smaller than that. We are still, believe it or not, in the macro world, comparatively speaking. To get to the nanoscale, we have to go much smaller. Okay, let's move from things we can see to the microscopic world inside our own bodies. A single red blood cell, which is itself totally invisible to the naked eye, has a diameter of about 7,000 nanometers. Now we're getting closer. We've moved into the microscopic realm, but even a red blood cell is still pretty large. Remember, the upper limit for nanotechnology is 100 nanometers, so a red blood cell is about 70 times larger than that. And finally, to truly arrive at the nanoscale, we have to reach the level of life's most fundamental molecules. The iconic double helix of a strand of your DNA is only about 2 nanometers in diameter. This is the true scale of nanotechnology. When scientists are working in this field, they're building things with components the size of DNA, the size of proteins, of viruses. So, from a sheet of paper all the way down to a strand of DNA, that vast journey in scale is what separates our everyday world from the nano world.
That really puts it into perspective. Building on the scale of DNA is just incredible. So if the goal is to construct new things at that level, what are the main approaches scientists use to actually work at this scale?
That's a great question because it really gets to the how of it all. There are two main philosophical approaches, as you see here, bottom up and top down. The top down approach is probably more intuitive for us. It's essentially sculpture, but on a tiny scale. You start with a larger block of material, a silicon wafer is a classic example, and you carve, you etch, or you mill it down to create nanoscale features. This is really the workhorse of the modern electronics industry, and it's used to create the billions of tiny transistors on a computer chip. The bottom-up approach is the conceptual opposite, and it's where so much of the future potential lies. It's like building with Legos at a molecular level. Instead of carving away material, you start with individual atoms and molecules as your building blocks. Scientists design these components with specific chemical properties so that they will spontaneously self-assemble into larger, more complex structures. Nature is the ultimate master of this. Just think of how DNA and proteins form complex biological machinery. Nanotechnologists are learning to mimic and control that process to build from scratch.
It sounds incredibly complex, drawing on so many different ideas. What specific scientific fields does nanotechnology draw upon to make all this possible?
You're absolutely right. It is not an isolated discipline at all. Nanotechnology is a classic example of what we call a confluence, where multiple fields are completely interdependent on each other. So first, you have physics, which provides the essential understanding of quantum mechanics. These are the fundamental rules that govern how matter behaves at this scale. Then you have chemistry. Chemists are the molecular architects, really. They develop methods to synthesize the specific molecules and nanoparticles needed as building blocks. Biology plays a huge role, acting as a library of inspiration. It studies nature's own nanomachines, like proteins, which provide incredible blueprints for new nanodevices. Next up is materials science, which takes these components and creates brand new materials with unprecedented properties, like exceptional strength or new electronic capabilities. And finally, engineering ties it all together. Engineers design the amazing tools we need to see and manipulate things at this scale, and they construct the larger systems that use these nanoscale components. It's truly a team sport. That collaborative nature is fascinating. It really paints a picture of a field built piece by so many different experts. Let's dive into that a bit. It sounds like something from science fiction. So where did the initial idea for nanotechnology even come from? So if Feynman had this incredible vision, what were the specific inventions that acted as breakthroughs, the things that turned nanotechnology from a theoretical idea into a practical science? And once scientists could finally see and touch at the nanoscale, what were some of the first major building blocks they actually discovered?
That's the perfect way to frame it because it really was a journey from a vision to a practical reality. Its conceptual birth is widely credited to that famous 1959 lecture by physicist Richard Feynman. There's plenty of room at the bottom. He speculated about a future of manipulating individual atoms, building tiny machines, and storing vast amounts of data. Now, at the time, this was pure science fiction. The tools to do it simply didn't exist. Feynman had basically pointed to a destination, but science had no car, no map, no way to get there. The game-changing invention, the technology that provided the eyes and fingers to see and touch this world, came in 1981 when Gerd Binning and Heinrich Rohr invented the scanning tunneling microscope, the STM. For the very first time, we could create actual images of individual atoms. This was quickly followed up in 1986 by the atomic force microscope, or AFM. These tools literally unlocked the door to the nano world. And as soon as scientists had these tools, they started discovering entirely new nanoscale structures. In 1985, a new form of carbon called buckyballs was discovered. But the most significant discovery came in 1991, carbon nanotubes. These are cylindrical molecules of carbon that are incredibly strong and have amazing electrical properties. This combination of new tools and new materials created a perfect storm of innovation that fueled the explosion of research that's still going on today.
What a remarkable progression from a lecture to these groundbreaking tools and materials. A key theme you've mentioned a couple of times is that the very rules of matter seem to change at the scale. Why is that? What are the core principles that make nanomaterials so different? That is perhaps the single most important concept in all of nanotechnology. A material like gold, for example, is yellow and chemically stable when it's in a gold bar. But at the nanoscale, gold nanoparticles can appear red, they can act as powerful catalysts, and their melting point actually changes. This dramatic transformation is primarily due to two principles that completely take over at that tiny scale. The first is a massive increase in the surface area to volume ratio. The second is the dominance of quantum effects. In the world we see every day, these effects are negligible. You don't even notice them. But at the nanoscale, they become so pronounced that they fundamentally alter a material's most basic properties: its color, its reactivity, its melting point, and its conductivity. Understanding these two principles is really the key to everything. Okay, let's break those down. Could you elaborate on that first principle for us, the increased surface area to volume ratio?
Absolutely. The sugar cube analogy is perfect for this. So imagine a single solid cube of sugar. It has a specific volume and a specific surface area, just the 6 faces of the cube. Now imagine you crush that cube into a fine powder. The total amount of sugar, the volume, hasn't changed at all. But what has changed dramatically is the total surface area. Each of those tiny little grains has its own surface, and the sum of all those tiny surfaces is vastly, vastly greater than the original cubes. At the nanoscale, this effect is extreme. A much larger proportion of a nanoparticle's atoms are right there on the surface, exposed to the outside world. And the major consequence of this is that nanomaterials become far more chemically reactive, simply because chemical reactions happen at surfaces. With exponentially more surface available, the material can interact much more efficiently with its surroundings. We actually exploit this to create things like highly efficient catalysts or to break down environmental pollutants.
That makes perfect sense. More surface just means more space for action. So what about the second principle you mentioned, the dominance of quantum effects? What does that mean for these materials?
This is where things get really fascinating and, frankly, a little weird. In our everyday world, objects are governed by predictable classical physics. But when you get down to the nanoscale, the counterintuitive rules of quantum mechanics take over. One of the most important consequences of this is a phenomenon called quantum confinement. So, in a large piece of metal, for instance, the electrons can possess a smooth, continuous range of energy levels. They have a lot of freedom to move around. But when you confine those same electrons within the tiny space of a nanoparticle, their freedom is severely restricted. Their available energy levels are no longer continuous. They become discrete or quantized. They can only exist at specific separated energy levels. And this quantization of energy levels has profound direct consequences. It fundamentally changes the material's most important electronic and optical properties. It dictates how the material absorbs and emits light, which is what determines its color. It changes how it conducts electricity. By simply changing the size of the nanoparticle, you change the degree of confinement, which in turn changes those discrete energy levels. This gives scientists an unprecedented level of control. They can literally tune a material's properties, like its color or its conductivity, not by changing the material itself, but simply by changing the size of its particles. It's like having a set of tuning knobs for the fundamental properties of matter itself.
Wow, that's a mind-bending concept.
Tuning a material's color just by changing its size. Can you give us a real-world example of these quantum effects in a product we might know? Yes, absolutely. There's a perfect and very popular example, quantum dots. These are tiny semiconductor nanocrystals, often just a few nanometers in size, made up of only a few hundred or maybe a few thousand atoms. They are a direct commercial application of that quantum confinement principle we just discussed. They're specifically engineered to be so small that these quantum effects completely take over and dictate their behavior. And here's where it gets amazing. The color of light that a quantum dot emits when it's energized depends directly and predictably on its physical size. It's an incredibly precise relationship. Just as the slide shows, the smaller dots confine electrons more tightly, which causes them to emit higher energy, bluer light. As the dots get progressively larger, the confinement is less severe, and so they emit lower energy, redder light. By precisely manufacturing quantum dots of different sizes, engineers can produce any color in the visible spectrum with incredible purity. And you can see this technology in action in a product many people have in their homes right now: QLED TVs. QLED stands for Quantum Dot Light Emitting Diode. In these displays, a layer of these quantum dots is placed in front of an LED backlight.
When the blue light from the LEDs hits the quantum dots, they absorb that light and then re-emit it as pure red, green, or blue light, depending on their size. This allows the TV to create a much wider and more accurate range of colors. So those rich, vivid colors you see on those high-end screens are a direct result of harnessing quantum mechanics at the nanoscale. That's a fantastic real-world example. It really connects the dots, no pun intended, between quantum theory and my living room. Let's broaden our view now. Moving from principles to practice, how is nanotechnology being applied in the critically important field of medicine? The impact on medicine, a field now often called nanomedicine, is one of the most exciting areas, for sure. A foremost application is in targeted drug delivery. Traditionally, when you take a drug, it kind of floods the entire body, which leads to all sorts of side effects. With nanotechnology, scientists can design nanoparticles to act as tiny biological delivery trucks. They encapsulate a drug and are then coated with molecules that act like a key, programmed to bind only to diseased cells, like cancer cells. This delivers the medicine exactly where it's needed, which improves effectiveness and drastically reduces collateral damage. The most famous recent example of this, of course, is the lipid nanoparticles that were used to protect and deliver the fragile mRNA molecule in the COVID-19 vaccines. Beyond that, nanotechnology is revolutionizing diagnostics with nanosensors that can detect disease biomarkers in the blood for much earlier diagnosis. And in medical imaging, nanoparticle contrast agents are making MRI and CT scans much, much clearer and more detailed. Besides medicine, which is obviously huge, what are some of the other major areas where nanotechnology is making a significant impact today?
Well, the impact is incredibly broad. While medicine is a huge area, you can see from this chart that the largest current application is actually in electronics, making up over a third of the market at 35%. That's followed pretty closely by energy and environmental tech at 30%, and then a whole range of consumer products that we use every single day, which account for about 25%. It's truly becoming a general-purpose technology. In electronics, the impact has been foundational for decades now. Moore's law, the observation that the number of transistors on a chip doubles roughly every 2 years, is fundamentally a story of nanotechnology. The constant shrinking of those transistors is a top-down nanofabrication process. It's also critical for data storage. The ability to store terabytes of data on modern hard drives is thanks to nanoscale magnetic materials. And as we've just discussed, it's the science behind the superior color of next-generation displays like QLEDs. In the energy and environment sector, the contributions are just as critical. Nanomaterials are used to create coatings for solar panels that are much better at absorbing sunlight, which improves their overall efficiency. For energy storage, nanotechnology is right at the heart of battery innovation. By creating nanostructured electrodes, we can vastly increase the surface area inside a battery, which allows for higher energy density and much faster charging times. And for the environment, nanoporous membranes can filter out the tiniest contaminants from water, while other reactive nanoparticles can be used to break down industrial pollutants in groundwater. And finally, it's in so many consumer products you might use every day without even realizing it. Many modern sunscreens use nanoparticles of zinc oxide or titanium dioxide. At the nanoscale, these materials are transparent to visible light, but they still block harmful UV rays, which is why they provide that great protection without that thick, white residue of older sunscreens. Nanoscale coatings are on eyeglasses to make them scratch-resistant, on car paint to make it water-repellent, and on building windows to make them self-cleaning. It's even woven into textiles to create stain-resistant and wrinkle-free clothing by changing the surface properties of the individual fibers. It's truly astonishing how this invisible science is so visible in our world once you know where to look. To wrap things up, looking at everything from Feynman's vision to QLED TVs, what would you say is the ultimate takeaway? What is the overall significance of nanotechnology? I think the overarching significance is that it represents a really profound shift in how we engineer our world. For all of human history, we have been limited to working with materials in their bulk form, mixing them, melting them, shaping them. But now we're moving beyond that. We are transitioning from simply manipulating bulk materials to being able to precisely control and construct matter right at the atomic and molecular level. It's a new industrial revolution, but it's happening at the smallest possible scale. And the main takeaway from all this, I think, is that by leveraging the unique principles that only exist at the nanoscale, that high surface area and the dominance of quantum effects, we have unlocked a toolbox to create completely new properties in materials. We are no longer limited by the materials we find in nature. We can now design materials to have the exact properties we need. We can make an inert material reactive. We can change a material's color without using any dyes. We can make an insulator into a conductor. This ability to dial in specific functions by controlling structure at the atomic level is the core power of nanotechnology. And because of this incredible power, nanotechnology is not just another technology. It is a foundational platform for innovation, much like electricity or the internet were in their time. It's what we call an enabling technology that will underpin breakthroughs in countless other fields. As our ability to build at this incredible scale continues to improve, nanotechnology will undoubtedly be at the heart of the solutions to some of humanity's most significant challenges, from developing new cancer treatments to building the next generation of computing. It truly proves that the biggest revolutions often come in the smallest packages.
Thank you for that powerful summary. It's so clear that this isn't just about making things smaller, it's a completely new way of building our world from the atoms up. By harnessing the strange rules of quantum mechanics and the power of increased surface area, we're unlocking capabilities that are already transforming medicine, electronics, and energy. We've seen how this incredible journey started with a visionary idea from Richard Feynman and was then made real by these incredible tools that let us finally see and touch individual atoms. It really is an invisible revolution with very visible results, and this has been a fantastic foundation for our exploration. This has been an incredible foundation for our series.
In our next episode, we'll explore tools and techniques for nanofabrication. We'll get to look at the sophisticated instruments and processes scientists use to actually build these incredible structures. I want to extend a huge thank you to our guest for sharing his expertise with us today. Thank you for tuning in to Tech, AI, and Beyond. Don't forget to subscribe for more insightful episodes. We'll leave you with this to ponder. What great challenge will nanotechnology solve next? Thank you for joining our exploration.